Gravity is not a force. I know that bothers some of you. I can see it on your faces already. You came in here thinking you understood gravity, at least roughly. Maybe you remember it from high school. Maybe you remember Newton and the apple. Maybe you remember the equation F equals G times M1 times M2 over R squared. And you thought, okay, that is a force. It pulls things together. End of story. And I am telling you right now, before we go any further, that picture is wrong. Not a little wrong. Not approximately wrong, fundamentally, deeply, structurally wrong. And the fact that it works, the fact that Newton's formula lets you send a rocket to the moon and land it within a few feet of where you planned, that is one of the great seductions in the history of physics. It seduces you into thinking you understand something that you do not understand at all. Let me tell you where I am coming from. I have spent more than 50 years thinking about the structure of physical law. I helped build string theory. I fought Stephen Hawking for 25 years over whether information gets destroyed in black holes, and I won that argument, although it took until 2004 for Hawking to finally admit it. I have spent decades working on the holographic principle, which says that the information content of a region of space is proportional not to its volume, but to its surface area, which is one of the strangest and most powerful ideas in all of physics. And through all of that, every road, every argument, every calculation keeps coming back to gravity. Gravity is not just another force sitting alongside electromagnetism and the nuclear forces. Gravity is the odd one out. Gravity is the one we do not understand. And until we understand gravity at its deepest level, we do not understand the universe. So let me strip this down to first principles. That is what I always do. I do not care what you think you know. I care about what is actually true. And I care about building it from the ground up so that every brick is solid before we put the next one on top. Here is the ground floor. You are sitting in a chair right now. You feel something pushing up against you from below. Your intuition says that is because Earth is pulling you down, because gravity is a force that reaches out from the center of the planet and grabs you and tugs on you. Newton would have told you the same thing. And for 200 years, that picture was good enough. But then along came a kid from the Swiss patent office, a guy who had failed to get an academic job, a guy whose professors thought he was a mediocre student. And that guy, Albert Einstein, blew the whole thing apart. Einstein did not start by trying to fix gravity. That is important. He started by thinking about elevators. I am not joking. This is 1907, and Einstein is sitting at his desk in Bern, and he has what he later called the happiest thought of his life. Here is the thought. Imagine you are in an elevator, and the cable snaps. You are in free fall. Everything around you is in free fall. Your keys, your coffee, your pen, everything floats. You feel weightless. Now here is the question that changed physics. In that moment of free fall, can you tell the difference between floating in that broken elevator and floating in deep space, far from any planet, far from any star, with no gravity at all? The answer is no. You cannot. There is no experiment you can do, no measurement you can make that will tell you the difference. And if you cannot tell the difference, then maybe, Einstein said, there is no difference. Maybe what you call gravity is not a force pulling you down. Maybe gravity is something else entirely. Now, sit with that for a moment, because most people blow right past it. This is not a metaphor. This is not a philosophical musing. This is a physical principle, and it has a name. It is called the equivalence principle. And what it says is devastatingly simple. It says that gravitational acceleration and the acceleration of your reference frame are the same thing. They are physically, experimentally, completely indistinguishable. And if they are indistinguishable, then you have no right to call one real and the other fake. You have no right to say gravity is a force that exists out there in the world, and the other thing is just an artifact of your motion. They are the same thing. And the moment you accept that, the moment you truly internalize it, the entire Newtonian picture of gravity collapses. Let me give you a thought experiment to make this concrete. Suppose I put you in a room with no windows, sealed box. and I tell you that you are standing on the surface of Earth, feeling your normal weight. You feel yourself being pulled toward the floor. Now suppose I am lying. Suppose you are not on Earth at all. Suppose you are in deep space, and the room is a rocket ship accelerating upward at 9.8 meters per second squared. The floor pushes up against your feet with exactly the same force. Your coffee sits in the cup exactly the same way. You drop a ball and it falls to the floor at exactly the same rate. You cannot tell the difference. There is no experiment, no measurement, no clever trick, nothing you can do inside that room that will tell you whether you are in a gravitational field or an accelerating rocket. That is the equivalence principle. And Einstein took that and ran with it for 8 years. And what he came out with on the other side was general relativity, which is not a theory of gravitational force. It is a theory of curved space-time. Here is where it gets strange, and I promise you, it really does get strange. If gravity is not a force, then what is it? Einstein's answer is that gravity is geometry. Gravity is the curvature of space-time itself. The Earth does not reach out and grab you with some invisible hand. The Earth, by virtue of its mass and energy, warps the fabric of space-time around it, and you, sitting in your chair, are simply following the straightest possible path through that curved geometry. You think you are being pulled down. You are not. You are moving through curved space-time, and what you feel as gravity is actually the floor of this room pushing up against you, preventing you from following your natural path, which would be free fall. I want you to really hear that because it is counterintuitive and it matters. In general relativity, the person in free fall is the one who is not accelerating. The person in free fall is following what we call a geodesic, which is the straightest possible path through curved space-time. You, sitting in your chair, being held up by the normal force of the floor, you are the one who is accelerating. You are being accelerated upward, away from your natural geodesic, and that acceleration is what you feel as weight. Gravity, in Einstein's picture, is not a force at all. It is the natural geometry of the universe, and what we experience as gravitational effects are what happens when something prevents us from moving freely through that geometry. Now, I know some of you are thinking, fine, that is a nice reinterpretation, but does it actually make different predictions? Is this just philosophy? No, it is not philosophy. And this is the part where Einstein went from being a genius to being something more than a genius, something I do not have a word for. He worked out the mathematics of curved spacetime using the tools of differential geometry that had been developed by Bernhard Riemann 50 years earlier. Riemann was a mathematician who had figured out how to describe curved spaces of any number of dimensions, and he did it for purely mathematical reasons, not because he thought it had anything to do with physics. And then Einstein came along and said, this is not just mathematics. This is the actual structure of the physical universe. Space and time are not a flat stage on which physics happens. Space and time are themselves dynamic, curved, shaped by the matter and energy they contain. And he wrote down the equations, the Einstein field equations, that tell you exactly how matter curves space-time and how curved space-time tells matter how to move. Let me read you the equation. I am not going to write it on a board. I am just going to say it. R mu nu minus 1/2 G mu nu R equals 8 pi G over C to the fourth times T mu nu. That is it. That is the whole theory. Everything about gravity, everything about the large-scale structure of the universe, the expansion of space, the bending of light, the existence of black holes, gravitational waves, all of it comes from that one equation. And I want you to feel the weight of that. One equation written down by a single person in 1915, and it has survived every experimental test we have thrown at it for over a century. It predicted the bending of starlight by the sun, confirmed in 1919 by Arthur Eddington. It predicted the precession of Mercury's orbit, which Newton could not explain. It predicted gravitational redshift, confirmed in the Pound-Rebka experiment in 1959. It predicted gravitational waves, confirmed by LIGO in 2015, 100 years after Einstein wrote the equation. It predicted black holes, which people thought were mathematical curiosities until we started finding them everywhere. One equation, one person, and the universe obeyed. Now, here is where I have to get personal for a moment because this is where my own life intersects with this story. When I was a young physicist, I was not particularly interested in gravity. I was working on particle physics, on the strong force, on quarks and gluons. Gravity seemed like a solved problem. Einstein solved it. End of story. But then, in the early 1970s, something happened that changed everything. And it happened because of Jacob Bekenstein, who was a graduate student of John Wheeler at Princeton. Bekenstein did something that most established physicists thought was crazy. He suggested that black holes have entropy. Now, entropy is a thermodynamic quantity. It is related to heat, to disorder, to the number of microscopic ways a system can be arranged. And the idea that a black hole, which is supposed to be a pure gravitational object described entirely by Einstein's equations, could have entropy, could behave like a thermodynamic system, that was wild. It was genuinely wild. And most people dismissed it. But then Stephen Hawking, trying to prove Bekenstein wrong, accidentally proved him right. Hawking showed that black holes radiate, they have a temperature, they emit particles, and that discovery, Hawking radiation, opened up a can of worms that we still have not closed. Here is the can of worms. If a black hole radiates, then it eventually evaporates. It shrinks and eventually disappears. And when it disappears, what happens to all the information that fell into it? The stuff that made the black hole in the first place, the star that collapsed, all the quantum information encoded in every particle of that star, where does it go? Hawking said, it is destroyed, gone, erased from the universe. And I said, no. I said, that cannot be right because the destruction of information violates the most fundamental principles of quantum mechanics. Quantum mechanics says that information is always conserved. The universe never forgets. You can scramble information, you can spread it out, you can make it impossibly hard to recover, but you cannot destroy it. And I fought Hawking on this for over 2 decades. I fought him at conferences. I fought him in papers. I fought him in arguments that got heated enough that people would stare at us. And I was right. Not because I am smarter than Hawking. I am not. Hawking was one of the greatest minds of the 20th century, but because the principle of information conservation is deeper than any particular theory of gravity. Quantum mechanics wins. And when Hawking finally conceded in 2004, when he gave his famous talk at the GR17 conference in Dublin and admitted that information is not lost, that was one of the most important moments in the history of theoretical physics. But here is the thing that keeps me up at night. Hawking conceded that information is conserved, but we still do not fully understand how it gets out. The mechanism by which a black hole returns information to the rest of the universe as it evaporates, that is still not completely worked out. We have made enormous progress. The work on the Page curve, on quantum extremal surfaces, on the island formula, these are breakthroughs that have happened just in the last few years, and they are stunning. But we do not have the complete picture. And the reason we do not have the complete picture is that we do not have a complete quantum theory of gravity. And that brings me to the deepest problem in all of physics. General relativity is a classical theory. It treats space-time as a smooth, continuous fabric. Quantum mechanics, on the other hand, says that everything at the fundamental level is discrete, probabilistic, uncertain. And when you try to combine these two frameworks, when you try to write down a quantum theory of gravity, things go badly wrong. The calculations blow up. You get infinities that you cannot remove. The standard tricks that work for electromagnetism and the nuclear forces, the tricks of renormalization, they fail for gravity. Gravity is non-renormalizable. And that means that our two deepest theories of physics, general relativity and quantum mechanics, are fundamentally incompatible at the deepest level. They cannot both be exactly right. Something has to give. Now, I have spent a large part of my career working on this problem, and I believe that string theory offers the most promising framework for resolving it. In string theory, the fundamental objects are not point particles, but tiny vibrating strings. And one of the vibrational modes of these strings corresponds to the graviton, which is the quantum particle of gravity. String theory automatically includes gravity. It does not have to be put in by hand. Gravity falls out of the mathematics naturally, and when you calculate gravitational scattering amplitudes in string theory, the infinities go away. The theory is finite. It is well defined, and that is remarkable. No other approach to quantum gravity has achieved that. But I have to be honest with you, string theory has not been experimentally confirmed. The energies at which stringy effects become important are far beyond what any conceivable accelerator can reach. And there are aspects of the theory that we do not fully control, particularly the question of the landscape, the vast number of possible solutions, and the question of how to select a particular solution that describes our universe. These are open problems, and I would be lying if I told you they were close to being solved. Let me come back to gravity itself, because I want to make sure you see the full picture. I started by telling you that gravity is not a force. It is geometry. Now, I want to tell you something even more disturbing. Gravity might not even be fundamental. There is a growing body of evidence, much of it coming from the holographic principle and from the work of people like Juan Maldacena, Mark van Ramsdonk, and others, that gravity might be emergent. That space-time itself, the very fabric of the universe, might emerge from something deeper, something that is not spatial at all. The idea is that space-time is woven out of quantum entanglement, that the reason distant regions of space are connected, the reason you can travel from here to there, is because the quantum degrees of freedom associated with those regions are entangled. And when you remove the entanglement, space itself falls apart. It literally tears. It disconnects. This is not speculation. Van Ramsdonk showed this explicitly in 2010 using the tools of the AD-CFT correspondence, and it sent shock waves through the field. Let me unpack that because I realize I just said something that probably sounds insane. Here is the idea. Start with a quantum system that lives on a boundary, a lower dimensional surface. This quantum system has no gravity. It is an ordinary quantum field theory, the kind we use to describe particles and forces. Now, the holographic principle, the ADAS CFT correspondence that Maldacena discovered in 1997, tells us that this boundary quantum system is exactly equivalent to a higher dimensional gravitational system in the interior. Same physics, different description. The boundary theory has no gravity, no space-time geometry in the usual sense. The interior theory has gravity, has curved space-time, has black holes and gravitational waves and all of it. And these are not two different theories. They are the same theory written in two different languages. Gravity, space-time, the whole geometric picture, it is an alternative description of quantum entanglement on the boundary. And that means, at the most fundamental level, gravity is not a fundamental force. It is not even a fundamental aspect of reality. It is a way of talking about the entanglement structure of quantum information. I want you to feel how radical that is. For 400 years since Newton, we have thought of gravity as something out there in the world, a real force or a real geometric feature of space-time. And now there is serious, rigorous, mathematically precise evidence that gravity is an emergent phenomenon, that it arises from something deeper, that space-time itself is not the fundamental arena of physics, but a derived, emergent, approximate description that breaks down at short enough distances or high enough energies. The fundamental thing is quantum information. The fundamental thing is entanglement. And gravity, space-time, geometry, all of it is how that quantum information organizes itself at large scales. Now, let me give you a thought experiment that brings this home. Imagine you have two entangled particles. Quantum mechanics says that measuring one instantly affects the other, no matter how far apart they are. Einstein hated this. He called it spooky action at a distance, but it is real. We have tested it thousands of times. Now, here is the deep insight. Take a large quantum system with many parts, all entangled with each other in a complicated pattern. The geometry of the entanglement, which parts are most entangled with which other parts, defines a kind of distance. Parts that are highly entangled are close together. Parts that are barely entangled are far apart. And this distance, this measure of closeness defined by entanglement, turns out to look exactly like the distance in a gravitational spacetime. The more entanglement, the more connected the space. The less entanglement, the more separated things are. And the dynamics of how that entanglement changes, how it evolves and rearranges, those dynamics look exactly like Einstein's equations of gravity. The Einstein field equations emerge from the rules of quantum information. That is one of the most profound discoveries in the history of physics, and most people have never heard of it. Let me tell you a story about how this played out in practice, because the history matters, and I was there for some of it. In 1993, Gerard Hooft, who had won the Nobel Prize for his work on the strong force, proposed something strange. He suggested that the physics of a three-dimensional region of space can be completely described by a theory living on its two-dimensional boundary, like a hologram. You look at a hologram and you see a three-dimensional image, but all the information is actually encoded on a two-dimensional surface. Tooft was suggesting that the entire universe works this way. I took that idea and ran with it. I developed it into what became known as the holographic principle, and I published a paper in 1995 laying out the argument. At the time, people thought it was interesting, but maybe just a curiosity. And then, in 1997, Maldacena dropped the bombshell. He showed a concrete, mathematically explicit example of holography in action, the ADS CFT correspondence, and suddenly the holographic principle was not a speculation anymore. It was a theorem, or as close to a theorem as we get in physics. And that changed everything. Now, I need to be careful here because I do not want to leave you with the wrong impression. The holographic principle and AD-CFT have been worked out in detail for a particular kind of spacetime called anti-de Sitter space, which has a negative cosmological constant. Our universe, as far as we can tell, has a positive cosmological constant. We live in de Sitter space, not anti-de Sitter space. And extending holography to de Sitter space, to cosmology, to the actual universe we inhabit, that is one of the great unsolved problems of theoretical physics. We do not know how to do it. We have ideas, we have proposals, we have some partial results, but we do not have a complete holographic description of our universe. And that bothers me. It should bother you too. Because if holography is truly a fundamental principle of nature, and I believe it is, then it should work for our universe, not just for a mathematical idealization of it. The fact that we cannot make it work yet tells me there is something deep that we are still missing. Let me shift gears and talk about something that has actually been measured, because I have been in the clouds for a while, and I think it is important to come back down to Earth, literally. Gravitational waves. Einstein predicted them in 1916, 1 year after he published general relativity. He showed that his equations admit wave-like solutions, ripples in the fabric of space-time that propagate at the speed of light. But the effect is tiny, unimaginably tiny. Einstein himself was not sure they were real physical phenomena or just mathematical artifacts of the equations. There was a famous debate about this that went on for decades. And it was not settled until 2015 when the LIGO collaboration detected gravitational waves for the first time from two black holes spiraling into each other and merging more than 1 billion light years away. Think about what that means. Two black holes, each one with a mass dozens of times the mass of our sun, spiraling around each other at nearly the speed of light, getting closer and closer, and in the final fraction of a second before they merge, they radiate more energy in gravitational waves than all the stars in the observable universe combined are radiating in light. All of that energy converted into ripples in the geometry of space and time traveling across a billion light years of space, arriving at Earth, and stretching and squeezing the 4-kilometer arms of the LIGO detector by a distance of about 1,000th the diameter of a proton. 1,000th the diameter of a proton. The fact that human beings built a machine sensitive enough to detect that, I find that genuinely awe-inspiring. That is not a word I use casually. And gravitational wave astronomy is not just a technological triumph. It is a completely new way of observing the universe. We have been looking at the universe with light for 400 years, since Galileo pointed his telescope at Jupiter. We added radio waves, X-rays, gamma rays. We expanded the electromagnetic spectrum, but it was always the same basic thing, photons. Gravitational waves are not photons. They are not electromagnetic radiation of any kind. They are ripples in spacetime itself. And they tell us about things that light cannot, like the merger of black holes, which produce no light at all. The universe has been rumbling with gravitational waves since the Big Bang, and for the first time in history, we can hear it. We are listening to the geometry of the universe vibrate. That is not poetry. That is literally what is happening. And let me tell you something about what gravitational waves have already taught us that Newton could never have imagined. When those two black holes merged, the final black hole that formed was lighter than the sum of the two that went in. About 3 solar masses of material were converted entirely into gravitational wave energy. 3 solar masses converted into ripples in geometry. That is Einstein's E equals mc squared at the most extreme scale imaginable. Mass became geometry. Matter became space-time vibration. If that does not make the hairs on the back of your neck stand up, then you are not paying attention. And we are just getting started. The next generation of gravitational wave detectors, LISA in space, the Einstein telescope in Europe, Cosmic Explorer in the United States, these will be orders of magnitude more sensitive. They will hear black holes merging at the edge of the observable universe. They will detect the gravitational wave background from the Big Bang itself, the primordial ripples in space-time from the first fraction of a second of cosmic history. We are about to open a window onto the birth of the universe that has been sealed shut for 13.8 billion years. There is another aspect of gravity that I want to make sure we cover because it is fundamental and it connects to everything else. Gravity is universal. That sounds like a cliche, but think about what it actually means. Electromagnetism only affects charged particles. The strong nuclear force only affects quarks and gluons. The weak force only affects certain particles under certain conditions. But gravity affects everything. Everything with energy, everything with momentum, everything with mass. And since E equals mc squared, everything with energy has mass, so gravity really does couple to everything. Photons have no mass, but they have energy, and they feel gravity. Neutrinos have almost no mass, but they feel gravity. Even gravitons, if they exist, would feel gravity. Gravity talks to everything, and everything talks back to gravity. And that universality is not an accident. In Einstein's framework, it is inevitable because gravity is not a force acting on objects. It is the geometry of the stage on which all objects move. Of course, everything feels it. Everything moves through space-time. There is no opting out. And that universality is precisely why gravity is so hard to quantize. When you quantize electromagnetism, you can separate the electromagnetic field from the other fields. You can do perturbation theory. You can calculate corrections order by order, and the answers converge. But gravity couples to everything, including itself. Gravitons carry energy, and energy gravitates. So gravitons interact with gravitons, interact with gravitons, and the whole perturbative machinery spirals out of control. The infinities pile up faster than you can remove them. That is what non-renormalizability means in physical terms. It means that gravity's universality, its greatest strength as a classical theory, becomes its greatest weakness when you try to make it quantum mechanical. The very thing that makes Einstein's theory so beautiful and so powerful is the same thing that makes it resist quantization. That is not a coincidence. That is a clue. And I believe that clue is telling us that the right approach to quantum gravity is not to quantize general relativity, not to take Einstein's equations and jam quantum mechanics into them, but to find a completely different framework from which both quantum mechanics and gravity emerge as limiting cases. That framework might be something like string theory. It might be something we have not thought of yet, but it is out there, and finding it is the most important problem in theoretical physics. Now, let me come back to something I said earlier and push it further, because this is where it really gets strange, and I have been waiting to say this. I said that gravity might be emergent, that space-time might be woven out of entanglement. If that is true, then the gravitational waves that LIGO detected are not fundamental ripples in a fundamental fabric. They are collective excitations of quantum entanglement. They are patterns in the way quantum information rearranges itself. The geometry that is rippling, the space-time that is vibrating, that geometry is itself a derived quantity, a large-scale description of something deeper. And that means gravity, even at its most dramatic, even in the violent collision of two black holes, is still telling us about quantum information. It is all information, all the way down. I am going to say something now that I have been thinking about for a long time, and I am not sure I have it right, but I am going to say it anyway, because that is how progress works. You say things, you put them out there, you argue about them, and eventually the truth emerges. Here it is. I think the reason gravity is different from the other forces, the reason it is so weak, the reason it is non-renormalizable, the reason it resists quantization is that gravity is not actually a force at all. Not even in the sense of being a gauge force like electromagnetism. Gravity is the thermodynamics of space-time. It is the macroscopic description of the statistical behavior of microscopic degrees of freedom that we have not yet identified. Just as temperature is not a fundamental quantity but emerges from the random motion of atoms, and pressure is not a fundamental quantity but emerges from atoms bouncing off walls, gravity is not a fundamental interaction but emerges from the collective behavior of whatever the fundamental degrees of freedom of quantum gravity turn out to be. Ted Jacobson showed something remarkable in 1995. He showed that you can derive Einstein's equations, the full Einstein field equations, from thermodynamics, from the relationship between entropy and area, the Clausius relation, and the equivalence principle. That is it. You assume that entropy is proportional to area, you apply the Clausius relation, you use the equivalence principle, and out come Einstein's equations, the equations of gravity derived from thermodynamics, not from an action principle, not from a Lagrangian, not from any of the usual machinery of fundamental physics, from thermodynamics. And thermodynamics is never fundamental. Thermodynamics is always the large-scale description of something microscopic, always. So if Einstein's equations are thermodynamic equations, then gravity is not fundamental. Gravity is emergent. And the microscopic theory from which it emerges is whatever the correct theory of quantum gravity turns out to be. This is the landscape I work in. This is the frontier. And I want to be honest with you about what we know and what we do not know, because there is nothing worse than a physicist who pretends to have answers he does not have. We know that general relativity is correct at large scales. Every test, every measurement, every observation confirms it. We know that quantum mechanics is correct at small scales. Same thing. Every test confirms it. We know that these two theories are incompatible at the fundamental level. We know that the incompatibility becomes important at the Planck scale, at distances of about 10 to the minus 33 centimeters and energies of about 10 to the 19 GeV, which is far beyond anything we can probe experimentally. We know that black holes pose deep puzzles about the nature of information, and that resolving those puzzles requires understanding quantum gravity. We have strong theoretical evidence from string theory, from holography, from the study of quantum error correcting codes in the context of ADS-CFT, that space-time is emergent and gravity is thermodynamic. But we do not have the final theory. We do not have the microscopic description. We do not have the fundamental degrees of freedom identified and the exact rules for how they behave written down in a complete and experimentally testable form. I want to close with something that I think is the most important point of all, and it is not a technical point. It is a point about how to think. Gravity is the thing you think you understand. You have lived with it every second of your life. You have never experienced a moment without it. It is the most familiar thing in the universe, and it is the thing we understand least. It is the deepest mystery in all of physics, not because it is complicated, although it is, but because it sits at the intersection of everything. Gravity is where quantum mechanics meets general relativity. It is where information theory meets geometry. It is where thermodynamics meets the structure of space-time. It is where the smallest things we know about, quantum bits of information, connect to the largest things we know about, the expansion of the universe, the formation of galaxies, the structure of the cosmos on its biggest scales. Gravity is the thread that runs through all of physics. And when we finally understand it, really understand it, at the deepest level, we will understand not just gravity, but the nature of space, time, matter, and information. We will understand what the universe is made of and why it is the way it is. And we are not there yet, not even close, but we are closer than we have ever been. The ideas are sharper, the mathematical tools are more powerful, the experimental capabilities are greater than at any point in the history of science. LIGO is detecting gravitational waves. The Event Horizon Telescope has imaged a black hole shadow. We have mathematical dualities that relate gravity to quantum mechanics with extraordinary precision. We have a generation of young physicists who are not afraid to question the foundations, who are not afraid to tear down the assumptions and rebuild from scratch. And that is exactly what is needed, because the problem of gravity is not going to be solved by being safe. It is not going to be solved by incremental improvements to existing theories. It is going to be solved by someone who is willing to look at the foundations and say, that is not good enough, let me try something new. That is what Einstein did. That is what Newton did before him. That is what the next breakthrough will require. So here is what I want you to take away from this. The next time you drop your keys and they hit the floor, I want you to remember that you just witnessed one of the deepest unsolved problems in all of science. You just watched space-time curvature in action. You just watched what might be quantum entanglement expressing itself geometrically. You just watched something that connects to black holes and the Big Bang and the holographic principle and the nature of information itself. You think you watched your keys fall. What you actually watched is the universe doing something that nobody on this planet fully understands. Not me, not anyone. And I find that not depressing, but thrilling, because it means there is still something enormous left to figure out. And figuring things out is the whole point. That is why we do this. That is why I've spent my life on it. Not because the answers are comfortable. They are not. But because the questions are real and they are worth everything. And if you leave this room and you think about gravity the same way you thought about it when you walked in, then I have failed. Because the point is not to give you a prettier version of the same old story. The point is to show you that the story you knew was the prologue, and the real book is still being written, and some of you might be the ones to write it.